This video is a test prep for a organic chemistry unit test or the organic chemistry diploma. The only difference between the diploma and your unit test will be the number of questions. A lot of this video will refer to diplomas, but again, everything is equally valid for tests. So this is the breakout and emphasis by unit on the diploma exam when you're writing it. So if you're doing the organic or preparing for the organic chemistry piece, you'd be expecting about 12 of the 60 questions to be on organic chemistry. So a much more focused question set. On a unit test, you're going to get more questions per outcome than the diploma would have. I'm going to run through all the general outcomes. There are some other outcomes that might show up on a test or diploma, but these are the ones that are most likely to be there. So I'm not talking about sort of the lab specific type of questions or STS outcomes. So there's two general outcomes in every unit of chemistry. The first outcome for organic chem is students will explore organic chemistry as a common form of matter, and we'll go through each of these outcomes one by one, and I'll give some advice or focus and examples of each. The second set of outcomes is much more reaction focused. The first set that I'm about to go through, general outcome one, is the drawing, writing, interpreting what functional groups are there in organic compounds type of questions. So the first outcome is really a general intro of what is considered an organic molecule. So an organic molecule must contain carbon, but there's a few examples of carbon-containing molecules that are inorganic that aren't deemed to be organic. So you have to watch out for carbonates. So these are compounds with CO3 2-. Now the diploma won't just have that anion. It's going to be buried in with some other positive ion with it. So you might have sodium carbonate, 2 sodiums to go with the 2- carbonate. So that would be considered to be not organic. I don't need the charge at the end. Okay. You might also have cyanide, so Cn-. You could have sodium, lithium, potassium with cyanide. Carbides don't show up on diploma exams that often, but these are carbon with metals. So if you see this sort of weird symbol, and WCA, it's probably a carbide, but look for a metal. And then you've got the oxides of carbon that show up in complete and incomplete combustion. So carbon dioxide isn't deemed to be organic, nor is carbon monoxide. So we have a little piece of a question from a released item, the 2019, I think, and you're asked which of the following of these are organic. So we've got carbon in the first one, but that's CO2, so that's not organic. The second one has carbon, and it's not any of those we just talked about, so that's organic. There is an acid, carbonic acid. It's got that CO3 2-. Here we do have carbon, and we don't have an oxide, a carbide, cyanide. That is organic. This is an organic halide. This has shown up a few times. It might look like it's maybe an alcohol, but there's no carbon here. That's CO, that's cobalt, so no carbon, not organic. There's cyanide buried in with sodium, so not organic. We don't have any of those previously mentioned pieces here. This looks like it's going to be an ester, so that's organic. And we have a carboxylic acid. If you decode those double O's, C double bond O to O to H to H. I'll just clean up that messy H. So this, in fact, is organic. So you should be expecting a question on this, and hopefully you're quite successful. The next outcome, C1.2, a bit hard to study for. You may want to flip through your notes, or maybe the textbook might be more useful, and hopefully your teachers make connections between the organic molecules you're studying, whether they're aliphatic, aromatic, organic halides, alcohols, their connection to everyday life. So you have the oil industry, the fossil fuel industry, the heart of the Alberta economy. So that would be methane, propane as natural gases. You've got octane, sort of the heart of gasoline. Diesel fuel has a few more carbons in it, so you should be familiar with the connection of all of those. Vinegar is ethanoic acid, used in cooking. Benzene, a solvent. You've got your polymers, polyethylene, glucose, a sugar. Ethanol and alcohol. This is the alcohol you can drink when you're over 18. If you put 2 alcohols with ethane, that's antifreeze, a diol. So hard to study. Hopefully you've been paying attention to all the connections and you can handle those test or diploma questions. Okay. The next outcome, 1.3, is a big one, and I'll spend a little bit of time on this. You should be able to draw structures, the full structural diagrams like you did in Chemistry 20, condensed structures, lines, or molecular formulas using IUPAC rules for anes, enes, ynes, the cycloversions, aromatic with a benzene ring, organic halides, alcohols, and carboxylic acids and esters. So let's go through some examples of these. So alkanes are hydrocarbons with just C's and H's and no double bonds. So one of these simpler alkanes would be propane, prop meaning 3, and the ane ending tells us there's only a single dash between all the carbons. Now all of the alkanes have a carbon-hydrogen pattern. If I go CN, where N is the carbon count, there's always double plus 2 hydrogens to predict the molecular formula. So this alkane is C3, so I don't even need to count the H's. I just double 3 plus 2. So this would be C3H8. Okay. So molecular formula, we got the structural formula, condensed, C with 3 H's around it. Okay. In alkanes, unless there's a branch, you're going to see CH3 at the end, CH2s in the middle, and then a CH3 at the end. Now a branch will remove a hydrogen to form that branch. So CH3, CH2 in the middle, CH3 at the end. Line structures. To do these, I like to drop my pen and sort of loudly count. So if I put my marker down on the board and say 1, you can barely see a dot. I'm going to make a straight line. 2, move in an angle. 3, and that would be my 3 carbon. So I drop my pen, and every time I move it, I'm going to add a number, and that's my carbon count. So then I'm going to lift. So that's my 3 carbons. To help students decode these line structures, it helps if you put circles everywhere that there's an end of a line segment or an intersection. Okay, the green circles are not part of the answer, but they pop out the 3 carbons that are in this line structure. So I'll remove those green circles, but they're a nice tool for decoding lines. A quick example of in alkene. Sorry, I just have a typo here. Should be E and E, not Y. I put Y twice, so ALKENE. These are double bonds. I'll just do a real simple one, the smallest one possible. You lose 2 hydrogens in order to add in the double bond. This alkane is saturated. This alkene is unsaturated. The pattern here is CnH2n. So this is C2H4. The line structure looks a little weird. Just 2 carbons. So if I drop my pen and say 1, move it, 2, lift, That's my 2 carbons, and because there's a double bond, I have to put in a second line to show the double. So it looks just like an equals, the line structure for this particular ene. An alkyne now just has a triple bond. So that is 3 dashes, 3 pairs of electrons. I'll throw in a third carbon. This middle carbon has its 4 bonds, our end carbon has 1. The pattern when there's one triple bond is CN, H, 2N, and then we got to take away 2 more hydrogens to go from the double to the triple. So we go from 2N to 2N minus 2. So these are the generic formulas for alkanes, an alkene with 1 double, an alkyne with 1 triple. Line structure for this guy, 3 carbons. So I'll drop my pen and go 1, 2, 3, lift my pen, and this first spot has 3 bonds, so I have to triple up. Okay. So that's one way you could draw it. Now on an exam, you're going to see the proper Chem 20 bond angles. So from back in Chem 20, the central angle around this middle carbon would actually be 180 and straight. So I'll let my students not give me the proper bond angles, but the way you'd see this written on an exam is like this, straight. Again, it's Chem 20. You do not have to worry about any bond angles in writing your diploma exams or unit tests. It's not Chem 30 curriculum. So those are your aliphatic hydrocarbons. You can have cyclo. So I'll just do a sort of 1 or maybe 2 examples of a cyclo. You only have to worry about the anes and enes. So you have to have at least 3 carbons to have a cyclo. I'll do a 4th. Kind of looks like a box. And in naming these, you stick the word cyclo in front of the carbon count. The parent or the stem is the longest chain or the name for the ring. Okay, either one might have been used by your teacher. Again, parent or stem. So there's 4 here in a circle, so cyclobutane. Okay. This is also considered saturated, even though it's got less hydrogen than we see with the straight up alkane. This is a CnH2n generic formula. So it kind of looks like an alkene. They have the same molecular formula, okay, but still saturated. The line structure, this is just a box. Okay. Again, the end of every line segment is our carbons. So 1 there, 1 there, 1 there, and 1 there. Moving on, I'll just do one example of a cyclo. You've got aromatics. So these are a big classification of organic compounds that have a benzene ring somewhere. So a benzene is a 6-membered ring or 6-carboned ring where there are these delocalized electrons. We often draw benzene with a double, single, double, single, double, single type of pattern, but it's not the truth. It's just chemists having come up with a better notation. So there isn't actually a double and a single. There's actually a bond and a half. Okay? But if you see this, that makes a compound aromatic. This by itself is benzene, but realize on average there's only 1.5 bonds, not the double, single. Okay. So there's really on average a bond and a half here, a bond and a half here, all the way around. Later I'll talk about in some comments from the bulletin, but you're not asked whether this is saturated or not, so you don't have to worry about that with aromatics. Okay. This is still a hydrocarbon, but again, not aliphatic aromatic, so you'll see the word benzene added at the end. Okay, little confusing. You see this ene ending, but again, there is no actual double bond. Okay? And you can have different alkyl groups put in front or halogens, and you'll see those added in front based on the position. If there's just one of them, you don't need a number. So let's stick a chlorine on. It doesn't matter where I put it. I'll stick it on the bottom because I have room there. Okay. There's no rule that says start from the top or the bottom. You just start from whatever group has been added. So we have a chloro. Okay. This by default is the 1 position, but we don't need this number because there's no second group to count to, so don't put in the 1. Okay. If there is another chlorine, then we are going to need some numbers. Okay, we now have 2 chloros, so this is a dichloro. We're not going to go chloro-chloro. Okay? If it was a chlorine and a bromine, then we'd have to go bromo-chloro, and I just did that alphabetic. Okay? But they're both chloros. We use these prefixes, di, tri, tetra, if there's 2, 3, or 4 tetra. Now, because I have a di and there's 2 chlorines, we need to know where they are. Are they next to each other, 1, 2? Are they 1, 3, so a little gap in between them, or as far apart as possible, sort of top, bottom, 1, 4? So these are next to each other, so they're in the 1, 2 position. So this is 1, 2 dichlorobenzene. Again, lots of families to go through. Organic halides. We've added in halogens, chlorine, fluorine, bromine, or iodine. These I typically name quick if you're good with your rules with the alkanes, alkenes, alkyne branches. This is typically easier. So if you have something that looks like an alkane, it's not, or it will not be when I'm done. So we have 3 carbons, all single bonds with I added a chlorine to it in the middle. So 3 carbons, propane, but this is going to be a hydrocarbon derivative because there's not just C's and H's. We have this chloro. Okay. And the chlorine, theoretically, it could be at the beginning. Okay, it could be on any one of these carbons. We have to know which carbon it is. Is it on one of the ends, which would be the 1 position, or in this case, it's in the middle, which is the 2 position. So this is 2-chloropropane. The line structure, 3 carbons, so we just like propane that I believe I did before. Drop my pen, go 1, 2, 3, lift my pen. That's propane, but not the first, but the middle carbon here. We have a chlorine. So you have to put in letters other than C and H's in line structures. So when I do the branches or alkyl groups, I drop my pen on top of a carbon, but I say 0 because I'm on top of a stem or parent carbon. Move my pen up 1, lift. So this would be a methyl unless I write something in here, but I will put a Cl to show that there is no carbon at the end of that line segment. So sometimes students incorrectly think there's a carbon there and then a chlorine, but no, if the end of a line segment has a letter, it is that atomic symbol that matches that letter or letters. A few more families left. Again, this is a big part of the course. You're going to get a lot of unit test questions or even a few diploma questions from this outcome. So alcohols have a OH group attached to the carbon chain. This is a hydroxyl group. Make sure you don't call it hydroxide. That is an ion. It makes something basic, but this is hydroxyl and an alcohol. So this particular alcohol has 2 carbons, so ethane, and then we add the OL ending to tell the reader it is an alcohol. Now often you have to add a number in between the N and the OL. In this case we don't. Because this is at a N position, and in this particular small molecule, either carbon would be at an end. So this is kind of ethane 1-all, but we drop the 1 because it has to be at the end. There's no need of the number 1. An example of a carboxylic acid. If you've done acid-base equilibrium, you would have seen lots of these acids. So at an N carbon, you have a C double bond O, a carbonyl, and a hydroxyl group. So you've got kind of two functional groups combined together into one. Now the carboxyl group, the combination of these two functional groups, must be at the end. Because this carbon, in order to have those two functional groups, double bond, single bond, takes up 3 of the 4 bonds. So there's no way this can be in the middle. So it's always at an end. So you never need a number for this functional group in carboxylic acids. Again, because it's at the end. So 2 carbons, ethane, and the combination here, we add oic space acid. Okay. So that's our ethanoic acid, or our vinegar. A smell you're probably familiar with. Last, no, esters sort of first come up later in the course, typically when you get into your reactions, and then you have to name it. This is the only sort of compound that's made from 2 different organic derivatives. All the other reactions you'll study have just one hydrocarbon or hydrocarbon derivative. So you need to have a alcohol. We'll do the simplest alcohol, methanol. And that's going to react with a carboxylic acid. Now I like to color code these. So I'll make my acid red. So that's my acid and carboxylic acid. You do need an acid catalyst. Sulfuric acid or concentrated sulfuric acid will work well to drive this reaction. Now you don't need to know how it happens, but I find it useful for students to remember how to make esters by explaining the how. This is a polar bond. This carbon is slightly positive, and the lone pairs on this will end up attacking this carbon. Now it is more complicated than that, but we'll leave that to second year university organic to go into the more details and how the acid contributes, but that helps you get the connection right, and we'll see our ester and name it. So we've got the black piece, and the black H of the hydroxyl group will come off and make part of our water product, and then we've got our acid piece that makes the ester. And you end up losing 2 pieces that form a water. So in naming this, you kind of have to decode this and split it down the middle. You name the alcohol piece first. So it could be on the right, could be on the left. You kind of expect on a test or diploma, your teacher's probably going to put the alcohol piece on the right to sort of make sure you fully understand the rules. But the alcohol piece is the black piece. That's got 1 carbon. So we use the alkyl name from the alcohol, so methyl. And then we move on to our acid piece. So this is 2 carbons, and we use a alkane name. So ethane would be the 2 carbons. Drop the last E, and because this is an ester, we add the ending 08. I find it kind of a weird ending, but doesn't matter. We do what IUPAC tells us to do. So methyl ethanoate is the name of this ester. So I've kind of reviewed esterification from the next outcome. So that's your reaction types. You will be asked about identifying functional groups. So we have that hydroxyl group. So that is a OH covalently bonded dash to a carbon or a carbon chain, often referred to as an R. So make sure you do not identify hydroxide, the ion. Okay, that is not hydroxyl. So our hydroxyls will be with our alcohols. Okay. Carboxyl, this is a combination of 2 functional groups. Okay. We just went through this. We've got a carbon with a double bond O. carbonyl, and a hydroxyl. Okay. Now, one thing I like to mention, which is not assessed, is carbonyl, particularly for university, and just so you can keep that last carboxy separate. Carbonyl is just C double bond O with whatever carbons or a hydroxyl group coming off of it. So if you ever heard this word, make sure you keep it separate from carboxy. An ester linkage has an O that sort of came from alcohol to C with a double bonded O, and then continuing. Okay. So this is going to be in the middle of that alcohol piece in this particular case on the left, and then the carbons from the alcohol continuing to the right. Okay. Halide or functional group are just our halogens, fluorine, chlorine, bromine, or iodine in our organic halides. So here's an old diploma question, or at least a released item, asking you to identify functional groups in this molecule. So is there a methyl group? Well, methyl would have to be a branch, and there's no branches here. So there is no methyl. Carboxy is this guy, and we do have that in this piece of the molecule. Ester linkage might look like we kind of see two O's, C double bond OO, but that end hydrogen would have to be a carbon in order for that to be an ester linkage. So it's close, but not quite. And halogen, yeah, we've got a fluorine. Okay, so we've got a couple of the sort of Chem 30 functional groups that you need to be able to identify in that question. Define structural isomers. You'll never be asked the definition, but you will be asked to apply them. So I'll run through a really quick isomer type question. So I'm going to draw all the isomers of C4H10. Okay. Now I teach my students generic formulas, not that they'll get tested on them, but they really help with isomers. So anything that's an ane is a CnH2n plus 2. Anything that has one double bond will be CnH2n. So to make the double, you lose two hydrogens. A ine with only one triple bond, you take away two more H's. If something is a cyclo with all single bonds, cycloane, it starts similar to an ane, but in order to make the ring, you've got to lose two H's to complete the ring. So it's CnH2n. And the last that you would want to consider is a cycloene. So if you start with the ane, you've got to take out two H's to make the ring, and you've got to take out another two H's to put in the double bonds. So it's CnH2n minus 2. So we see some repeating patterns. Anes don't repeat with anything. The ines and the cycloanes have the same pattern, and the triple bonds, the ines and the cycloenes, repeat. So in considering isomers, you're going to consider red, green, or blue, the way I've color-coded it. So in this example, we're a CnH, let's see, 4. We have to double to 8 plus 2 would be 10. So this is a 2n plus 2. So in considering the isomers for C4H10, we are only going to consider anes. There's no way it's an ene, an ine, a cycloane, or cycloene. There's not enough hydrogens in any of those possibilities. So in drawing the isomers, I start with the longest chain or parent and then work my way down. So I start with all 4 of them in a row. I'm going to skip putting in all my H's for the sake of speed. I'm just going to put dashes in. So there's a hydrogen there, there, 2 in this middle, 2 in this middle, and then 3 on the end. That's my 10. So that would be a butane. No other straight chains, there's no doubles or anything else to add in. So then I move down to, is there a 3 long chain or parent that I can do with some branches? And there is. I can't put a branch on the end, either end, because that would be part of the longest chain. The only spot I can put a branch and keep the prop is to put the carbon in the middle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That works. So this is a methyl. I don't need a number because it can't go in the 1 or the 3 position. The 3 is never allowed, and either would be the 1, and that's not allowed. So it has to be the 2 position. So this is methyl propane. And for this example, there are only 2 isomers. Okay? Likely you might get a question where it's the green or the blue case, and I would tackle, if you've got a 2N hydrogen count, do all the enes and then do all the cycloanes, or if you have a 2N minus 2. So the 2N minus 2 might be like C5H8. Okay, not a lot of hydrogen, so you're going to consider the 2 blues. Okay, so work through a whole sort of type of family and then work through the other. Okay, so that is isomers. Annoyingly on diplomas, you're probably going to be asked how many isomers there are because you can't draw them. So in this case, the answer would be 2. And unfortunately, if you miss just 1 isomer, you will get 0 on the diploma. You'll have the incorrect count. So you really need to perfect this skill. A half knowledge in this skill, unfortunately, won't help you with diplomas. Might help you if unit tests, if you have a written response and your teacher gives you part marks. So we're through a lot of the first general outcome. You should be able to do boiling points within a homologous series. So within a homologous series, you're looking within a series of maybe anes or enes or ines. Okay. So I have a few members of a straight chain ane series: propane, ethane, pentane. Okay? And you need to think of your Chem 20 forces. You've got London dispersion forces, dipole forces potentially, or hydrogen bonding. Okay? If you have a organic hydrocarbon, you're only ever going to have to worry about London dispersion forces. Hydrocarbons, C and H only, do not have dipole or hydrogen bonding forces. So these are all members, not consecutive, but they all are members of the same homologous series. So the lower the electron count, in essence, the smaller it is, the less London dispersion forces it'll have. So we need to list this from highest. So what has the most London dispersion would be the biggest with the most electrons. So that'd be pent in this case. So that would be the highest. Second most electrons, really can just use carbon count as a proxy, would be our prop. And third would be our eth. Okay. So whether they're consecutive members or there is a gap in between, it doesn't matter in applying the London dispersion forces to the series. Okay. You should also be able to do it with sort of different types of families that are going to have different forces. So I'm going to rank propanoic acid, propene, and propanol from lowest to highest. So I flipped the ordering that I want here. So what do we have here? We have a acid. Okay, this acid is going to H bond. It has all the forces. Okay, so it's got that OH that can H bond, but it's also got that carbonyl C double bond O that's quite polar. So that's going to beat this alcohol that only has the OH. Okay, and then we've got our propene with just London dispersion forces. So our lowest forces would be propene, just London dispersion. Then we've got the propanol is going to come next. Okay. Similar London forces in all of these. They're all 3 carbon long. They're not all the same. There's some oxygen count difference, but big gap here between 1 and 2. And then the propanoic acid with the OH that the alcohol has plus the extra polar piece would have the highest boiling point. Okay, so all the questions are sort of going to fit into these 2 categories: homologous series, or they're going to have different functional groups, and you got to remember your Chem 20 forces. Okay. Fractional distillation has shown up on I think every diploma I've seen. This is year 13 for me looking at diplomas. Solvent extraction is much more rare. So this is an exact diagram of fractional distillation. You absolutely, again, need to know this. Totally shocked to not see it on a diploma. In fractional distillation, they are heating at the bottom. And this diagram doesn't show it, this diploma diagram, but they're cooling as you go up. So only the lowest boiling points will make it up through the cooling and make it to the very top. So you're going to have the smallest hydrocarbons with the lowest boiling point making it to the top. Okay. So I'm not going to write the word hydrocarbons, but smallest is at the top, the largest. With the largest in size, with the largest London forces will come out the bottom. The things like tars, asphalt, very large hydrocarbons will never even boil and they'll just melt and come out the bottom. Okay? So if you're given a list of hydrocarbons, you need to apply your boiling point properties. Occasionally you'll see solvent extraction, almost never a decade ago, but a little more often now. Again, you're using your boiling point solubility type of skills. You need to know your forces. So if you have, maybe you have butane in the ground, C4H10, and you want to extract this butane from the ground, you'd have to realize that butane is a hydrocarbon. It has London dispersion forces only. If you want to send a solvent into the ground to extract this out, you need to have something that's going to be soluble with it. You'd want something else that only has London dispersion forces. You'd want to use another hydrocarbon that would dissolve this and then bring it out of the ground. If you try to put water into the ground to dissolve this, it's not going to. Water is hydrogen bonding. It is London dispersion, dipole, and hydrogen bonding. It's going to totally repel butane, and it's not going to be able to act as a solvent and extract it. So you're looking for high solubility in solvent extraction. Okay? But again, make sure you know fractional distillation. So that's all of general outcome 1. General outcome 2 is a much shorter list, but there's just so much buried in this first outcome that even though the list is shorter, there's still a lot to know. So I'll just quickly go through these reaction types: addition, substitution, elimination. I break into 2 types. You don't have to know these 2 words. You can classify them both as elimination. But again, there are different reaction conditions. Esterification we already talked about, so I won't recap that again. That's your alcohol and carboxylic acid making your ester. In combustion, complete and incomplete. Okay. And then we've got some other sort of polymer type questions that are likely to show up. So let's sort of dive into these, the general outcome 2s. So I'm putting outcome 1 and 2, or 2.1 and 2.2 together to be able to illustrate these reaction types and write and balance them. So addition reactions. I'll keep things fairly simple. I'll add a third carbon here. Additions need to have a double bond or a triple bond. The first bond between any 2 atoms is really strong, and they're called sigma bonds, and they don't break very easily. But the second bond is a different type of bond. It's in different 3-dimensional space, and it's much weaker. So I like to color code it and to remind students that that's the weak one that can break. If you wonder why don't these other bonds break, they're fundamentally a different bond, a much stronger bond. So you can get that bond to break and add something to it. So I'll add HF. So when this bond breaks, we have bonding capacity freed up on both sides of this bond, so at the end and at the middle. And this H from our HF could add to this carbon or that carbon. We're going to have 2 possibilities of how this adds. So we end up getting 2 different named products in this case. You do have to be careful. Sometimes when it adds either way, it has the same name, so you only have to do it once. Okay. But in this case, if we have, we have the breakage on the left-hand side, we could add the F in the middle and the H there across the old double bond, or we could do it the other way, getting a 1-fluoro or a 2-fluoro option. I'm just going to dash out the other carbons and not write them in for the sake of time. So the end of all these dashes are a carbon. So I'm not doing a proper structure. So we've got our 2-fluoro propane on the top, our 1-fluoropropane at the bottom. These are isomers of each other. There are 2 products. I'm going to put a plus. In high school, we're not learning the ratio of these two. We're just learning to write all possible products. So that's our addition reaction. There's either 1 or 2 answers to all addition problems. Okay? Sometimes due to symmetry, these two are the same name. Substitution reactions. There's sort of 2 types, but I'm only going to go through one. You really just tend to see one type, where you're substituting a hydrogen away with UV light. So we'll start with propane. And I'll write in my 8 H's, C3H8. That's that 2N plus 2 pattern. I'll add bromine to it. You do need ultraviolet radiation. These are those sigma bonds that are really strong, so they're not going to break if you just dump in bromine. But with ultraviolet radiation, you get some radical chemistry that we're not studying, but you can get one of those H's to pop off. Okay. Now we have a couple possibilities. We could have an H pop off at the very end, or we could have an H pop off in the middle. Either one will give us a different name product. So I'll do the one at the end first. So this H can go. One of the bromines can take its place and would get a 1-bromo product. Okay. And one of these other diatomic bromines gets left over. And we have an H popped off. So we get an HBr inorganic product. So that's one possibility of our substitution, 1-bromo propane. We also have the middle position that the bromine could add. So this is our 2-bromo product. Again, I'm not putting in all the H's. Okay, for the second possibility, we also have a leftover Br and an H. You might think, okay, there's 2 bromines here. Can't one do the first and one do the second? They can't. The mechanism that makes this happen is UV light is going to create some radicals with this bromine and make a bromide, okay, which is this guy. Okay, and that bromide won't cause a second step or a second reaction. So we've got all our products, our 1-bromine, our 1-bromo propane, our 2-bromo propane, our 2 HBRs or hydrogen bromides. But just to finish balancing this, we actually need 2 of our organic compounds, and we need 2 of these. And now we have a nice balanced substitution reaction. Okay. And this is the most common substitution that you're going to see on your diplomas or your unit tests. Okay. A few other reaction types we've got to go through. Elimination. There are 2 types here that you need to know. They're quite different, so it's a bit annoying that they're both called eliminations, but they both are. It's just what gets eliminated. So you can have ones with organic halides. So here's our 2-chloropropane. You can eliminate this Cl, so get rid of it, and take an H off of one of the on either side and make an ene. Now to do this, you're going to need some sodium hydroxide to help pull off the H to make that double bond. So again, I'm going to circle some stuff. You don't need to know what I'm about to say. You just need to know the product. But this chlorine can come off. In university, this would be referred to as a leaving group. It's something that's stable on its own. When that leaves, one of the neighboring H's, it's got to be one carbon away, can also be removed. And this is where you need the hydroxide to help this or to make it happen. So when this happens, we have 3 carbons left over. The Cl and the H goes, so we get a double bond. The other hydrogens stay put. So we go from an ane to an ene, and then we've got a few other products. The sodium and the Cl will make sodium chloride. So the chlorine becomes chloride, and you get a water between the H that came off and the OH. So that's one of our elimination types. The other type of elimination you can get, it's fairly similar, but it's with a alcohol and a hydroxyl group rather than a chlorine. So this is dehalohydrogenation because you're removing an H and a Cl. This is a dehydration. You don't have another reactant, but you do need an acid catalyst. You need an acid that's sort of big and bulky that isn't going to add when we remove things. Okay? That's just going to help pull off the H. So same type of circumstance. Our 3 carbons are going to end up with a double bond. Our acid is going to help remove this, and then to either side, we're going to remove an H. Now, in both of these examples, whether you remove it from the right or the left, it's in the one position. So that's why I'm only writing one product. But you always have to consider the right and the left. And if they have 2 different names, double bond here versus here, you would have to consider 2 products. Okay? But it's propene either way. So I'm drawing it once. Okay? So I'm choosing to put the double bond there. Again, I just as easily could have put it over here. So there's our propene, just like above. Okay, and you get a water product. So the acid helps pull off the OH, makes the water, and then the other H regenerates the catalyst. Okay, and that's why it is a catalyst and not a reactant. Okay, so on diploma exams, both of these, the dehydration on the bottom, the dehydrohalogenation on the top, you just call them elimination. Esterification, we already ended up doing, or I already did an example when I talked about ester, so I won't repeat that. But it's definitely worth talking about combustion for a second, and in particular, making sure you're aware of 2 types of combustion. So you've got what you should already know from Science 10, complete combustion. So I'm going to use methane as my fuel, plus oxygen, and complete combustion makes carbon dioxide gas and water vapor in open combustion. Okay. In thermodynamics, you'd study that if you have a closed system, like inside a cell, this is water liquid, but I'm doing open combustion and balancing this. I'm not going to really talk about this very much because this is just a repeat of Science 10. You need to be aware of incomplete combustion. And really just the products of incomplete combustion, and particularly their environmental consequences. So with incomplete combustion, you have a limiting amount of oxygen. So all of the carbon doesn't get fully saturated with oxygen. Some of it can, and if it does, you'll get carbon dioxide gas. That's a greenhouse gas. Some of it may only pick up 1 oxygen, which is carbon monoxide. Now, this is a toxic gas. You can't smell it, you can't taste it, and hopefully your home has a carbon monoxide detector in it to let you know if you have a leak likely in your furnace. And this product is why you do not run a barbecue or a stove in your house. You don't want to produce carbon monoxide in your house. Now you could get carbon not getting any oxygen, and you would get just soot, which is an air pollutant. Okay? Now this is going to come up in thermodynamics as much or more so than here. If you burn a food in a open combustion lab experiment, so maybe you burn a potato chip and you have an aluminum can over top and you collect it, you might see some soot, and that'd be a sign that you have incomplete combustion. Okay? And you can also get water vapor. Okay? So this is incomplete combustion. You should know it. Definitely know it for your diploma. But I'm kind of crossing thermodynamics and organic a little bit here. For years, they didn't really emphasize a lot of this outcome. They would just ask about addition polymers. And the addition polymers is what I've color-coded in yellow. Okay? Addition polymers is when you have an ene. So I'll do the simplest example, ethene. And you have tens of thousands or millions of these, and we're not going to put a big number, we're just going to say n, some big large number. This can polymerize. We've got this second bond here where the first one is a really strong sigma bond, but the second one can be broken, and in the right conditions it breaks and adds another one of these ethanes to it and creates a big long chain. Now there's no way I can write 100,000 of these together, so we just write a repeating pattern. In brackets, we'll put what repeats. Okay, and I'm going to put a dash through the brackets, and just another unit would add right next to it. We're going to get this 2-carbon repeating pattern. And in addition polymerization, you break the bond. And that's what creates, a bonding capacity coming out of each of those carbons. And that's the black, or what I'm about to make black in and out of the brackets. And we have 4 things connected to those 2 hydrogen, and in this case they're all H's. We have a monomer, ethene in particular is the name of this monomer, and we have a polymer. Okay, we don't call this a product, we call it a polymer. The name of these polymers is just poly stuck in front of the monomer. So this is polyethene. Okay. Can seem a little bit confusing because you see ethene, so you think, oh, there's a double bond, but no, there's not. The monomer had the double bond, the polymer doesn't. Okay. Now this isn't a testable thing, but these are your number 2 and number 4 plastic codes. Okay. And to make them sound better, often everyday society uses slightly different names. So polyethylene is the common name, but polyethene is the IUPAC name that you have to know. So that's the yellow addition polymers. And for years, that's all that was ever on the diploma. And that's all that I really emphasize to students. But now you also have to be aware of the red condensation polymers. Now these are complicated to draw, and I'm going to leave them out of this video, but this is when you have 2 different monomers. It's a type of esterification reactions. You need an alcohol, you need an acid, but you need 2 functional groups in the alcohol. So 2 OHs in the alcohol and 2 carboxys in the carboxylic acid, and you can add alcohol, acid, alcohol, acid, alcohol, acid. Okay. So the polymers, again, hard to draw, but you've got an alcohol piece, and then you've got an acid piece, and you've got another alcohol piece, and then you've got another acid piece. And it's just going to repeat over and over again and make a polyester. So you have to have a alcohol monomer, and you have to have a acid monomer, okay? And they have to be difunctional. So you need 2 OHs in your alcohol, and you need 2 carboxy groups. Okay, that's the only way you can get adding across the acid on both sides. Okay, so these are more common now than they used to be, And then to make this outcome even more complicated, you get a little bit of natural polymers showing up. Now, these are really just pure definitions. I want to say them orally. So carbohydrates, you can have monosaccharides, which lead to disaccharides. The disaccharides become the polymer carbohydrates. You have to be aware of those terms. Proteins, you've got amino acid monomers that can make DNA or RNA, which are the polymers. Okay, I would not worry about drawing these, but certainly be aware of those terms. So we've got addition polymers, we've got condensation polymers, and then we've got these sort of natural living, sort of memorize the terms with carbohydrates and proteins. So that's pretty much all the outcomes. The last one I'm not going to talk about much, but relate the reactions above to the production of thermal energy. So think of that as heat and its economic importance. So throughout the course, hopefully your teacher has connected the use of which organic compounds are fossil fuels. You've got your C1s to your C3s are your natural gases. C4 butane is a liquid at SATP, and all the way up to let's call it 12, 13, 14 are other common fuels, whether it's jet fuel, gasoline, diesel fuel. Okay, and obviously you burn those to get thermal energy. So not really an outcome you study for, but hopefully something you've picked up throughout this course. Last, the bulletin that's produced every year gives some comments that are well worth teachers and students paying attention to. So this is the trends in student performance and trends that are not going well that you should really be focusing in on and not repeating mistakes of people or students in front of you. So a bit of a warning that students are struggling with solvent extraction, fractional distillation. Every teacher should emphasize. I don't see a lot of solvent extraction, but when they do put it on, it is a struggle. Okay? And also the polymer section we just went through can often cause issues. When students are given the monomer, they can predict the polymer fairly well, but going backwards can be a bit of a challenge. So you might get a question where you're given this polymer. And I'll put 2 chlorines in the polymer. Okay, and you might be asked, what is the monomer, A, B, C, or D? So we got to work backwards. So we've got 2 carbons in our monomer, and then you just need to lock things in place and be careful not to move those CLs around. They're not on the same carbon, so we have to keep them in our monomer on different carbons. Okay. And then how do we go from this sort of ane structure to our monomer? Well, we need to have a double bond. This is clearly not a condensation polymer. There's no ester linkage. Okay. There's no O's in the middle, so this must be addition chemistry, so we needed a double bond to make this. Okay. So it's something you can be highly successful in. I've been consistently using the wording properly. Hydrocarbons are C and H only. If you see the term hydrocarbon derivative, there is something else added in, O or a halogen. X is sometimes used to represent halogens, and you should be used to the methods of organic compounds or benzene being written. You're going to see the line structure a lot on tests and diplomas. Either one of these are acceptable, but the circle is another way, and maybe a more accurate way that doesn't have double single to represent benzene. So make sure you're used to all of those. Okay. A note, again, hopefully you shouldn't have problems. Whenever you have a hydroxyl group, so that's an OH, you have alcohol. Now, if it's on a organic, originally, or a root that's our organic hydrocarbon, or an aliphatic carbon or hydrocarbon, we just refer to it as an alcohol. If it's on a benzene, you'll see the word phenol used. So here's my benzene. I'll put the circle in, and this would be phenol. on an aromatic. In determining whether something is saturated or not, we have a reminder that we're only going to look at the carbon-carbon bonds. So if we're asked whether this is saturated or not, this acid, I'm not going to put all my H's in, you just look at that stem or parent carbons. So there's our stem or parent. We do not factor in this double bond into whether it is saturated or not. So all our carbons have single bonds between them. It's full of hydrogen, so this is saturated. Okay. The sort of bromine test for whether something is saturated or not is a really common diploma question almost all the time. Okay. Something that's saturated must be an ane. Okay. And the anes cannot do addition chemistry, where if something is unsaturated, it's an ene or an ine. Okay. So the bromine test, so this is diatomic bromine, will be negative for this ane. Okay, so the bromine test is going to be an addition test. Okay, if you have a ene, you've got a double bond, so the bromine can react across that double bond, and you'll see a color change of the bromine. So you're really after the colors. So a student adds, this is a released item, a student adds bromine to a hydrocarbon sample. So we don't know what we have. Is it an ane? Is it ene? Is it an ine? We don't even know if it's aromatic or aliphatic, but it says hydrocarbons, not derivative, so it's CNH only. Okay. We know it's an isomer of this, so that's a CnH2n. So this is either a ene or a cycloane. Okay, but we're not sure. Okay, the student notices that the color of bromine changes from originally brown, orange to clear. So there must be a reaction for this to occur. So what could it react with? Well, it must have a double bond, so we must have the ene. Okay. So this must be unsaturated, and it would react with the ene. It would not react with the ane. Okay, so this again is trends in student performance. Students aren't rocking this question, but it is one that I would hope my students would find easy because I talk about it a lot. And it's just a color change type of question. If there's no color change, it's saturated. Now they do make a comment that bromine will react with an ane over a really long period of time. For bromine to react with an ane, this would have to be substitution, and you need UV light. And you can get UV light just coming from the sun. Okay, so if you have this reaction left out for a long period of time, for a day or more, enough will get through the glass. It'd be even faster if it was outside in direct sunlight, because glass blocks UV, that you will get a reaction. So they're just reminding you of that fact. But again, there's no immediate or fast reaction between an ane and bromine. I talked about whether something is saturated or not, and if it has a double bond or a triple bond, it is unsaturated. Okay, single bond between the carbon. Aromatics are like, well, there's this bond and a half, so what happened? So that's way beyond the scope of the course. You don't have to worry about aromatics and whether they're saturated or not for the sake of Chemistry 30. So that's a nice comment to clarify that, because the outcomes don't. Clarifying one of the original outcomes, general outcome 1, the third one, in terms of what you're asked to name and draw and decode. They can ask you questions about functional groups of compounds that you can't name, that you may not be sure how to draw. If they give you the name and the structural formula, so I did that here with acetyl salicylic acid, way beyond the scope of this course. You wouldn't know how to draw this, but you could be asked what functional groups are present. Okay, so you could identify this. There's a carboxy. Okay, here we've got another linkage that looks like an ester linkage. Okay, and you can identify those. Okay, there's no halogens here. Okay, and there's no double or triple bonds here. No carbon-carbon double or triple bonds. So just because you can't name it doesn't mean it's not fair game. And you always see these big, large molecules. Okay, this typically could show up as, is this aliphatic or aromatic? And they've, got a benzene ring here. So you'd call this an aromatic compound, not an aliphatic one. Just a comment, I'm curious they put this here. Hopefully you and my students wouldn't make this mistake, but just a reminder of what molecular formulas are. You've been using them since Science 10 or possibly even junior high. It's just counting the individual letters. A little bit of comment about solubility. For organic compounds to be highly soluble, there has to be it has to fit in one of two cases. So I'm going to really generalize this really quick. You could have substances that have London dispersion forces only, and they're going to be highly soluble in other substances that have London dispersion forces only. So these would be sort of our hydrocarbons or oils. So hexane and heptane would be highly soluble in each other. They're just hydrocarbons. The other possibility is substances that hydrogen bond will be highly soluble in other substances that hydrogen bond, and likely water is going to be involved here. Okay? Things that just have some polarity will have some solubility, but you're just going to get tested about highly soluble substances. So you're not going to refer to organic halides in water as being highly soluble. Okay? There's no hydrogen bonding in a organic halide, so not highly soluble. So it's kind of a little cookie cutter and simplified into these two camps. They kind of talk about that bromine test twice. It's coming up in another section and really emphasizing that color change, both with bromine that we kind of talked about before, or potassium permanganate will do the same thing of testing for whether there's a double or triple bond. So this is the exact same question that I put up again. Okay, so one way to analyze whether the reaction has happened is either to analyze, is there a color change in the organic compound, or is there a color change in the bromine that's being added? Okay, you can sometimes have two different layers, but if there's a color change, then you know that it is saturated and an ane or an ene. If there's no color change, if it's unsaturated, there'll be a color change. If it's saturated, there's an ane, and there'll be no fast reaction. Again, if you left it for 24 hours, enough UV would come in and it would happen. But they're talking about after shaking the sample. So that's a short period of time. There's no way UV light would have enough time to drive the reaction. We've got that color change we talked about. So we know it's unsaturated with that double bond. It is addition chemistry. That is fast. Okay? It is not substitution with UV light, which is slow, particularly when you just have light from the sun coming in to drive it. A comment, I'm going to do this quick. It's talking about hydrocarbon cracking fitting into the category of elimination. I don't see many hydrocarbon cracking, but this would be when you have a large molecule that you're going to split up. So maybe you have a C20H42, that's a 2N plus 2, so that's an ane, and maybe you break it up into, or you crack it into two C10s. Okay. And maybe the first one is an ane, C10H22, so the second one will only have 20 carbons left, so this is our ene. Okay. So we're still making an ene, so Alberta Ed is saying they're still classifying it as a elimination reaction. Again, I don't know if I've ever actually seen this classified, and I've rarely seen cracking questions, so I wouldn't put a lot of time into hydrocarbon cracking. Again, another question, I'm going to give a bit of my opinion on it, but it talks about two types of substitution reactions, but really the one with UV light that I've talked about that they highlight in yellow is the one that you're guaranteed to see on diplomas. The second type kind of is really similar to elimination, so I don't even want to talk about that, and I encourage you to just make sure you're familiar with a an ane with some halogen, okay, be it HCl or just a diatomic halogen, and that needs UV light, and that's the type of substitution you're guaranteed to see. Polymerization, I've really talked about this already, but you've got addition and condensation to study, and make sure you're good with both the monomer and the polymer and working backwards. And I did an example of already working backwards. 5 or 10 years ago, you could just study addition and you were good. You really didn't have to do anything else, but now you do have to worry about the condensation and those living polymers. So be prepared for those. And in this bulletin, they actually have a typo. They missed a few letters in their monomer here. This should be, I assume, polypropene and or chloropropene, creating polypropene. An addition polymer is mentioned in this bullet. So anyway, make sure you know both and you know the terms monomer, polymer. Naming the monomer is exactly the same as you've learned IUPAC rules. The polymer is poly, just stuck in front of the monomer, so you still have that ene following through. So I know this is a long recap, but hopefully that helped you study for organic. And this is part 1 of organic test and diploma prep. Part 2 will be me working through old questions.